Hi everyone. In this video, we're going to be talking a little bit about the matrix exponential. It's something that you may have encountered in your linear algebra or differential equations class, but we're going to take some time and go back and really understand what this is and how you compute it. So, to get started, let's get back to basics. What is the exponential function to begin with? So, what is e to the x where x is a real number? Well, we often think of this as some value, 2.71828, and so on, to the x power. But where did that come from? Well, it turns out that this was something that Jacob Bernoulli figured out, so one of the members of the Bernoulli family of mathematicians, in 1683. Figured out that you had some constant e, which is equal to the limit as n goes to infinity of 1 plus 1 over n to the n. Let's see, and this was while he was studying compound interest. So if you think about it, if you have money in a bank account every year it gains interest, well, when you multiply that by 10%, say 10% interest every year, when after 10 years, well, you don't have 200% of your original, you have 1 plus 1 over 10 to the 10th power. But what happens when you take that limit as n goes to infinity? So instead of having it compound every year, maybe you have it to compound every month or every day or continuously. And the natural logarithm and the exponential of the mathematical constant e come from studying that sort of behavior. So now, of course, we have this. So, well, what can you do? So, one thing you could do is, well, if you're taking it to a discrete power, like 2.71828, and this is dot 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 to the third, well, you just multiply it together 3 times. So this is equal to 2.71828 dot dot dot. We're going to ignore the fact that you're multiplying together a continued something that 28 dot dot dot. Okay, so you can just multiply together several times. Now, on the other hand, if you're taking a fractional power, well, we also know how to do this from our algebra classes. So let's say that's 3.1. Well, that's equal to 2.71828 dot 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 cubed times the 10th root of 2.71828 dot dot dot, right? Because it's the cube root times, the cube of e times the 10th root of e, and so on. So of course you could do this if you had, say, 3.14. So that's equal to the cube, 2.71828 dot cubed times the 10th root, 2.71828 dot 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 10th root times the 100th root to the 4th power of that 2.71828 dot dot dot. Okay, now if you want to take say e to the pi, well, this is equal to 2.71828 dot 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 3.14 dot dot dot. 14159. I don't actually have all pi memorized. No one does. And so you can take limits. So you can think of this as the limit as 2.71828 dot 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 goes to the x to the n power, where the limit as n goes to infinity of xn is equal to pi. So you could start with 3.1, 3.14, 3.14159, and so on. But this is kind of unwieldy. And so in calculus, we learned several other definitions for the exponential function, which are a lot nicer to work with, especially when you're doing proofs, but also even when you're doing computations. So the first definition, that we're going to talk about is as a solution to a differential equation. So you maybe recall that the derivative of e to the x is equal to e to the x. So let's call this definition 1. This turns out to be one of the super nice properties that comes from using e to the x and why it shows up so often. So e to the x is the unique solution. The unique solution to the differential equation d dx of y of x, so y is a function of x, is equal to y of x, and y of 0 is equal to 1. So basically we're defining e to the x as its own derivative, and we're saying at x equal to 0, at x equal to 0, e to the x has to be equal to 1. So that it matches some of the other properties of exponential functions. And this is a very nice definition to work with, and the one that one of the most commonly used properties of it. When you take the derivative of an exponential, you just get the exponential back. Okay, but there are a couple other definitions, and one of them has to do with this limit of continuous compounding. So e to the x is also equal to the limit as n approaches infinity of 1 plus x over n to the n. And this definition is very similar to this definition here. Basically, you're taking it to the x power, and so this is the definition as a limit of continuous compounding of interest. However, the definition that we most often use, and the one that's the easiest to generalize, is as a power series. So we have basically take the Taylor series of definition 1, and this will get you this Taylor series, or you can use it as a definition in and of itself. So let's say e to the x as m goes to infinity of x to the m over, actually let me change my limits to be as m goes to infinity. This will make our notation a little bit nicer later when we start talking about matrices that are n by n. Let me make all my limits actually xm. Okay, I think that's almost all the limits I had. Okay, I think that's changed all my limits. Okay, so as x to the m over m factorial. So this is as a Taylor series or as an infinite sum. Now, one of the things you might notice about this is that none of these definitions requires partial powers. All these are integer powers, integers m. So we can define the matrix exponential in this way. Let's go ahead and give another aside. So since e to the x is equal to the sum from m equals 0 to infinity of x to the m over m factorial, this, if you look at this power series, it turns out this has infinite radius of convergence. So we can use this definition for all complex numbers. So for all e to the z is equal to the sum from m equals 0 to infinity of z to the m power over m factorial, where z is a complex number. Okay? But now, you notice that the nice thing about this definition is that we don't have to deal with partial powers. And so this makes it a lot easier to define the matrix exponential, because you can just drop the same definition in, and, well, it turns out that it will work out just fine. So let's go ahead and talk about the matrix exponential. So matrix exponential. And we'll start with this definition 3, though we'll see that both of the other definitions also play a role in understanding the properties of the matrix exponential. So let's start with let e to the a, where a is a matrix, be equal to the sum from m equals 0 to infinity of a to the m over m factorial, where a is a complex n by n matrix, or a real one. And so, of course, since we're only taking integer powers of A, this can just be defined by repeated matrix multiplication. And this has a couple of nice properties that really match the definition of an ordinary exponential. So let's start with, I'm not going to go through all the properties of it since there are too many, but let's start with e to the 0 matrix is equal to the identity matrix. So as in before, when e to the x was, and we had x equal to a real number, e to the 0 was equal to 1. Here, it turns out that e to the 0 matrix, so where 0 is a 0 matrix, n by n. N by n is a 0 matrix. gives you the identity matrix that's also n by n. So that's really the equivalent property saying that e to the 0 is equal to 1. Furthermore, if AB is equal to BA, where A and B are n by n matrices, so if the matrices commute, then e to the x times e to the y is equal to e to the x plus y. And this is something you can verify by just using the Taylor series definition and adding things together. We're not going to do that in today's lecture, but that's something you should verify on your own time. And lastly, this is something we will verify. So if P is invertible, let's say P in C to the n by n is invertible, then e to the P inverse is equal to P e to the B P inverse. Okay, so let's see some of the consequences of this and also prove it along the way. So suppose that A is equal to P inverse. Well, then we have that A to the n is equal to P inverse. Oh, sorry, the inverse is inside there. Inverse to the nth power, which if you expand it out is P inverse times P inverse, dot, 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 all the way to P inverse. And this, of course, is n times. Actually, I'm using n for that, so we'll use m here, m times. And one of the things you'll notice is that P inverse times P appears inside of, well, you have a P inverse P repeatedly, and each of these is just equal to the identity because P is an invertible matrix. And so this entire thing is just equal to P B to the M P inverse. And so we can use that identity and substitute that into the Taylor series. So e to the a is equal to the summation from m equals 0 to infinity of a to the m factorial by the Taylor series definition. This is equal to the summation from m equals 0 to infinity of 1 over m factorial times p b to the m p inverse, which is equal to, if you pull out the p in front and the p inverse at the very end, this ends up being, by the distributive law, this ends up being p times the sum from m equals 0 to infinity of 1 over m times b to the m times p inverse. And of course, by the Taylor series definition, this is just p times e to the b p inverse, which proves the property 3 that we were discussing a moment ago. And this has some nice consequences. So, in particular, if you have a diagonalizable matrix, computing the matrix inverse is really quite easy. So let's say we have a diagonalizable matrix. Let's say this is A is equal to P inverse, where D is diagonal. So let's go ahead and let D be equal to D11, D22, all the way through DNN, and zeros everywhere else. I'm not always going to write the zeros in, but you should just assume that this is a diagonal matrix. So then, it's pretty easy to see that d to the m power is going to be equal to d11 to the m through dnn to the m, and zeros everywhere else. So we can write out e to the d using that. So e to the d is going to be the sum from m equals 0 to infinity of d to the m over m factorial, which is going to be, since all these are diagonal matrices, when you sum them together, you only get things that are different along, you get the sums along the diagonal. So you can pull the summation into the matrix. And you get the sum from d11 to the m over m factorial, and just all the sums along the diagonal. So m equals 0 to infinity of the nn to the m over m factorial. And of course, using the ordinary Taylor series definition, so the one back here, so for just a real or complex number, so that's this one here. Using that definition, you end up getting that this is just the diagonal matrix with e to the d11, e to the d22, all the way through e to the dnn. Which then implies that e to the a is equal to our p matrix times this diagonal matrix times P inverse, where of course A is equal to PD P inverse. And you will be using this particular property to, this particular result to compute the matrix exponential very often, because often you can diagonalize things, and if you can diagonalize things, then it turns out that computing the matrix exponential is entirely equivalent to just computing a diagonalization of the matrix and then multiplying together P, this exponential diagonal matrix, and P inverse. But now, what if A is not diagonalizable? So let's say non-diagonalizable A. Since not all matrices can be converted into a diagonal matrix, you don't always have an entire basis of eigenvectors. Sometimes you have to deal with generalized eigenvectors. And so for this point, we need to recall the Jordan canonical form. So let me just go ahead and state it again. Canonical form. Which is to say that every square matrix can, let's say, A in an n by n square matrix can be transformed into A is equal to, let's say, Pj P inverse, where note that J here is not the Jacobian matrix, which we may have seen elsewhere. I'm going to use J here to refer to the Jordan matrix. But anyway, P is a n by n matrix that's invertible. And J is equal to a block diagonal matrix where we have these Jordan blocks. Let's say we have little p of them. And this is block diagonal. And each J sub I is a Jordan block with some value lambda I. Well, this turns out to be one of the eigenvalues on the diagonal, but the fact that they're eigenvalues isn't actually super important for our purposes today. We just care about the fact that there is a Jordan decomposition, where you have lambda i's on the diagonal and one directly above the diagonal, and 0 everywhere else. Okay, so we have each of our ji's, so each of our sub-Jordan blocks is equal to lambda I, and so on. So lambda I is on the diagonal, and 1's above it. And 0's everywhere else. Okay, well, then we can apply the same argument. So then we have e to the a is equal to p e to the j p inverse by property 3 above. But note that e to the j is going to be equal to the sum as m goes from 0 to infinity of j to the m over m factorial, which is equal to this. We can move the sum into the matrices again. So this is the sum as m equals 0 to infinity of, and here this is a block diagonal matrix. And where we're taking advantage of the fact that the block diagonal matrix to a power is just the power of all the individual blocks and still in the same sort of block diagonal shape. So j1 to the m over m factorial, and so on. So this is the sum from m equals 0 to infinity of, this is j, what did I use? P. P was my variable, to the m over m factorial. And of course, although each of these are matrices, are blocks, you can think of them as matrices themselves. And so using the matrix exponential definition as a Taylor series, you get e to the j1 through e to the jp. So now we just need to compute the exponent of a Jordan block. So now suppose that ji is equal to lambda I through lambda I 1, 1. Well, this here is equal to the sum of this diagonal matrix, lambda I, and zeros everywhere else, plus the matrix that has zeros along the diagonal and ones above it. And so it turns out that, well, diagonal matrix commute with everything. And so what you can do is you can, let's see, so ji is equal to this. And if we want to take the matrix exponential of it, I'm going to use a slightly different notation. This is equal to, obviously we're just taking the matrix exponential of all of it, but since the diagonal matrix commutes with everything else, this implies that this is actually the exponential of lambda I times the identity, times the exponential of this matrix with zeros along diagonal and ones above it. Okay, and this is by property 2. So property 2. Let's go ahead and give this matrix a name. Let's call, I'm going to define a series of matrices. I'm going to call them n sub q, which are going to be q by q matrices. And they're going to be real, but since we're working with complex matrices, let's keep everything in the complex matrices. So these are q by q matrices, and I'm using the term n for nilpotent, which means that as you take matrix powers, eventually it'll all be 0, but that's a technical detail that you don't need to worry about. So we'll call this n sub q, and it'll be the q by q matrix with ones in the row above the diagonal and zeros everywhere else. So for example, if we had, actually what color was I using for examples? Let's use purple. So n4 is going to be equal to 0, 0, 0, 0, 1, 1, 1, and zeros everywhere else. 0, 0, 0, 0, 0, 0, 0, 0, 0. Okay? And notice that when nq squared is, when you multiply this out, and this is a fairly simple exercise in matrix multiplication, this has ones 2 rows above the diagonal and zeros everywhere else. Okay, and you can see this in the n equal 4 example. If you square this, this turns out to be the matrix where you have 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0. And you can see that just by matrix multiplication, and you can also see this in the general case. It turns out that when nq to the k has one's k rows above the diagonal and zeros everywhere else. And in particular, this means that nq to the q is equal to 0. Because once your q rows above the diagonal, you're off of the matrix. So this is the 0 matrix, which is also why we call these matrices nilpotent, because at some matrix power, you have just the 0 matrix. So now, one of the nice things about this, the fact that this is a nilpotent matrix, is that instead of having to take this infinite sum, you only have to take a finite sum, because everything above q is equal to 0. So plus the matrix exponential of nq, which is normally equal to the sum from m equals 0 to infinity of nq to the m over m factorial. This is equal to the sum from m equals 0 to q minus 1, nq to the m over m factorial. Because once you get above q minus 1, once you get to q, then you just get a 0 matrix, and you can add together 0 matrices without changing the sum, obviously. So this is just equal to I plus nq plus 1 over 2 factorial nq squared plus 1 over 3 factorial nq cubed plus plus 1 over q minus 1 factorial nq to the q minus 1. And this is now a finite sum, which makes it a lot easier to explicitly give the answer. And when we explicitly give the answer, this gives, well, I has 1 along the diagonal. So 1, let me actually draw this out a little bit bigger. So 1, 1, 1, 1. Yeah, so this says 1's along the diagonal. And in the diagonal above that, we have nq. So that's just the 1's along that there as well. So 1, 1. And what about the row above that? Well, you have 1 over 2 factorial n cubed squared. So let's see, that was this term. And let's put this in purple. So that means you have 1/2 for each of these terms. And in the next one, you have 1 over 3 factorial nq cubed. So you have 1 over 6 for each of these terms. Let's see, 1, 6, 1, 6, and so on. And of course, our last term here is just going to be 1 over q minus 1 factorial. And you're going to have zeros everywhere else. So this allows us to explicitly get the exponential of this particular nilpotent matrix, unless we are now able to compute, though it's a little bit of a pain, but we can compute. We can compute the exponential of a Jordan block, ji, which is equal to the exponential of lambda I times the identity. That's just the diagonal matrix, so taking the exponential, just taking the exponential of each of the diagonal terms, times this nilpotent matrix, n sub q sub I, where q sub I is the size of the ith Jordan block. Oh, sorry, you can't see that. Ith Jordan block. And thus, exponential of a, which is equal to p exponential of j, p inverse, is computable. So you just do this Jordan decomposition, and then you take the exponential of each of the Jordan blocks. Now, this is still a bit of a pain to do, because there's a lot of math involved here. Sometimes you might ask yourself, is there an easier way? And if you go back to these 3 definitions up here, originally we defined the exponential in several different ways. One was as the unique solution to a particular differential equation. Well, the differential equation of it being equal to itself. And it turns out you can use a very similar definition to a very similar identity to compute the matrix exponential using differential equations. So this is using definition 1, or something analogous to definition 1. It's not quite definition 1 because we're talking about matrices here. So what's another way of computing it? So let's say computing matrix exponentials using differential equations. Okay, so the first thing we need to do is let's recall that if you let dx dt be equal to ax, where A is a n by n matrix, and let's work in the reals for now just to make life a little bit easier for us, and x is equal to some function x of t, which is a length n vector. Well, then we know that x of t is equal to the value at 0, x naught, times the exponential of at. And this is something that you can prove using things like Picard iteration, or which you should have seen in a differential equations class. So you can prove this using things like Picard iteration proof. But we're not going to go into that. So suffice it to say that it turns out that the matrix exponential can be used to define, to give the solution to a differential equation as well. So if you knew the matrix exponential, you can expand, or you can expand the matrix exponential. Exponent of at is equal to the sum from k equals 0 to infinity of a to the k, t to the k. Oh, why did I suddenly start using k? Let's continue using m, just to keep life simple. A to the m, t to the m over m factorial to solve x of t. On the other hand, if we knew the solution, x of t, we can solve for the exponential of a t. And of course, then if you set t equal to 1, then that gives you the matrix exponential of e to the a. So you can go backwards here as well. And this is the inspiration for a technique that was given by Leonard in 1996 in the Siam Review. So I'll link it in the link below. But the basic idea here is if you let A be a n by n matrix and its characteristic equation, which is just determinant of lambda I minus a, is equal to lambda to the n plus a1 lambda to the n minus 1 plus dot 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 plus a n is equal to 0. So you have the characteristic equation. We can write a higher order ODE with constant coefficients. So we can write a higher order ODE with constant coefficients, which we know how to solve, which is going to be x to the nth derivative of x plus, actually let me write this in slightly different notation so that doesn't become too confusing. So d to the n dt to the n of x of t plus d to the n minus 1 dt to the n minus 1, so the n minus 1th derivative of x of t plus dot 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 plus d dt of x of t plus, oh sorry, I forgot my coefficients. So this is plus a1 times that, and this here is plus a n minus 1 d dt of x of t. plus a n x of t is equal to 0. So this is a higher order ODE that has that particular characteristic equation, which you can, of course, then solve to solve this particular equation. So when we can find n linearly independent solutions, x1 of t through xn of t, with initial conditions. So we need to be careful about what we're setting our initial conditions to be for each of our equations. So for x1, we have x1 of 0 is equal to 1, x2 of 0 is equal to, oh sorry, not x2, see, dt of x1 of 0 is equal to 0, and so on. And so d to the n minus 1, dt to the n minus 1 of x1 of 0 is equal to 0. So we have that, and we also have that for x2. x2 of 0 is equal to 0. Dt of x2 of 0 is equal to 1. D squared dt squared x2 of 0 is equal to 0, and so on, and the remainder are all 0. And so what you'll notice is that we're setting one of the, let's see, let me put these in boxes. Because these are the initial conditions for each of our solutions. And if we keep on going, we can go all the way to the end. And the very last one, we have xn of 0 is equal to 0, d dt of xn of 0 is equal to 0, and so on, all the way down to d to the n minus 2, dt to the n minus 2, xn of 0 is equal to 0. And for the very last one, d to the n minus 1, dt to the n minus 1, xn of 0 is equal to 1. Okay, so we set up our solutions with those initial conditions. Then it turns out, and I'm not going to go through with derivation in full, you can look up the source if you want to see the full derivation. Then e to the at is equal to x1 of t times the identity plus x2 of t times a plus all the way to xn of t times a to the n minus 1. And so basically by solving the system of differential equations, so if you know how to solve a higher order ODE and find all these different linearly independent solutions with different initial conditions, then you can also get the exponential of at. And of course, then if you set t equal to 1, then you can compute e to the a. Or often for differential equations, what you care about is actually e to the at. So I will leave off with an exercise for the reader, or reader, watcher, viewer. If you go back to the definitions, you'll recall that we gave 3 different definitions for the ordinary exponential. And now what we've done is we've shown that definition 1 and definition 3 can also be applied to matrices. What about definition 2? So the exercise for the reader is to verify that the alternate definition e to the a is equal to the limit as n goes to infinity of the identity plus, sorry, this should be m goes to infinity, the identity as I plus 1 over m a to the m also works. Okay, so that was a quick overview, a review of the matrix exponential, which you hopefully have seen before in either your linear algebra or differential equations classes. And in the next video, we'll be talking a little bit more about how we can apply this, again, to solving systems of linear ODEs. And we'll be giving an example that's actually from, giving a biological example of pharmacokinetics. So I will see you in the next video.